Hi, this is Muhammad Hafiz, and today I'm going to explain about the CPU scheduling in operating system. CPU scheduling is a fundamental concept in operating system that determines how the central processing unit CPU is allocated to the different processes or tasks. The two main types of CPU scheduling: number one, non-preemptive scheduling and preemptive scheduling. Non-preemptive scheduling. Definition. Non-preemptive scheduling is a CPU scheduling algorithm where a process that has been allocated the CPU continues its execution on the CPU until it either terminates or performs an I/O operation. The CPU is not taken away from the process until the process completes its own or voluntarily releases the CPU. Process flow. In a non-preemptive scheduling system, once a process starts executing on the CPU, it runs to completion without any interruptions. The CPU is allocated to the process until the process terminates or performs an I/O operation, at which point the CPU is then allocated to the next process in the ready queue. Non-preemptive scheduling process flow. Process arrival. A new process arrives, is added to the ready queue, waiting to be assigned to the CPU. CPU allocation. The process is selected from ready queue and allocated to the CPU. The process then begins executing on the CPU. Process completion. The process completes its execution on the CPU and either terminates or performs an I/O operation. The CPU is then available for the next process in the ready queue. Preemptive scheduling. Definition. Preemptive scheduling is a CPU scheduling algorithm where a process can be interrupted and moved to a waiting state to allow another process to run. The operating system can take the CPU away from a process and allocate it to other process based on a certain criteria such as priority or time slicing. Process interruption. In a preemptive scheduling system, a process can be interrupted and moved to a waiting state to allow another process to run. This allows the operating system to maintain a balance and ensure that all processes have a fair chance of accessing the CPU. Preemptive scheduling process flow. Process arrival. A new process arrives and is added to the ready queue, waiting to be assigned to the CPU. CPU allocation. The process is selected from the ready queue and allocated to the CPU. The process then begins executing on the CPU. Process interruption. The process system can interrupt the current process and move it to a waiting state to allow another process to run, based on factors such as priority or time slicing. Comparison of non-preemptive and preemptive scheduling. Non-preemptive scheduling. In non-preemptive scheduling, a process that has been allocated, the CPU continues its execution until it either terminates or performs an I/O operation. The CPU is not taken away from the process until the process completes its task or voluntarily releases the CPU. Preemptive scheduling. In preemptive scheduling, a process can be interrupted and moved to a waiting state and allow another process to run. The operating system can take the CPU away from a process and allocate it to another process based on certain criteria, such as priority or time slicing. Implications of non-preemptive versus preemptive scheduling. Turnaround time. In non-preemptive scheduling, process can experience longer turnaround time as they are forced to wait until the currently executing process completes. Preemptive scheduling can provide shorter turnaround time by allowing process to be interrupted and given a chance to run. Response time. Non-preemptive scheduling may result in longer responses for some time-sensitive tasks. Preemptive scheduling can offer better response times as it allows the operating system to prioritize urgent and high-priority processes, ensuring that they are executed in a timely manner. Key differences between non-preemptive and preemptive scheduling. Process interruption. Non-preemptive scheduling does not allow for process interruption, while preemptive scheduling enables the operating system to interrupt a running process and move it to a waiting state. turnaround time. Non-preemptive scheduling can result in longer turnaround times as processes are forced to wait until the currently executing process completes. Preemptive scheduling can provide shorter turnaround times. Response time. Preemptive scheduling can offer better response times by allowing the operating system to prioritize urgent or high priority processes, while non-preemptive scheduling may result in longer response times. Comparative illustration. Process arrival. A new process arrives and is added to the ready queue. CPU allocation. The process is selected from the ready queue and allocated to the CPU. Process execution. In non-preemptive scheduling, the process runs to completion, while in preemptive scheduling, the process can be interrupted and moved to a waiting state. Priority scheduling. In the realm of operating system, efficient process scheduling is paramount for optimal system performance and responsiveness. Priority scheduling, a widely used technique, assigns priorities to processes, enabling the operating system to manage and execute tasks based on their relative importance. Definition and explanation. Priority scheduling is an algorithm that executes processes based on their assigned priority levels. Higher priority tasks are given precedence to ensure critical work is completed first. The scheduler continuously monitors the ready queue and selects the highest priority process for execution. Key advantages. Priority scheduling offers several advantages, including the ability to prioritize time-sensitive tasks, ensure the timely completion of critical processes, and optimize system performance by giving preference to important tasks. Types of priorities. Priorities can be static, assigned to the time or process creation, or dynamic, allowing the changes based on factors such as resources usage or time spent waiting. Fairness concerns. While priority scheduling prioritizes important tasks, it is essential to ensure fairness by preventing high priority processes from monopolizing system resources and potentially starving lower priority process. Techniques such as aging or priority boost mechanism can be employed to mitigate the risk. Preemptive versus non-preemptive priority scheduling. Priority scheduling has two modes, preemptive and non-preemptive. Preemptive allows interrupting a running process for a higher priority one. Non-preemptive does not allow interruption even if a higher priority process arrives. Preemptive. In preemptive scheduling, the OS can interrupt a running process even if it has a higher priority. If a process with high priority arrives, the approach ensures that high priority processes are never delayed by low priority process. Non-preemptive. In non-preemptive priority scheduling, once a process begins execution, it continues until it completes or voluntarily yields the CPU. The OS will not interrupt a running process. Even if a higher priority process arrives, the approach is simpler to implement but can lead to starvation of lower priority processes. Priority-based non-preemptive scheduling. In non-preemptive priority scheduling, high priority process can run until completion. This is simpler but can starve low priority processes if high priority ones arrives continuously. Simple implementation, starvation potential, suitable for certain scenarios. This approach is simple to implement as it doesn't require the OS to constantly monitor the arrival of new processes and interrupt running ones. This makes it efficient in terms of computational resources. Starvation potential. A major concern with non-preemptive priority scheduling is a potential for starving. If high priority process continue to arrive, lower priority process may never go a chance to execute, leading to inefficient resources utilization and system delays. Suitable for certain scenarios. Despite its drawbacks, non-preemptive priority scheduling is suitable for scenarios where processes are relatively short and high priority processes are not frequently arriving, ensuring a smooth flow of tasks and minimal interruptions. Process selection and execution. In non-preemptive priority scheduling, the highest priority process runs until the completion even if higher priority ones arrive. CPU idle. The CPU is initially idle, waiting for the first process to arrive. Highest priority process selected. When a process arrives, the schedule